Good evening. For a long time now, we wanted to know whether there are planets going round other stars. Now remember, our sun's an ordinary star, one of 100,000 million stars in our galaxy alone. And many of those stars are very like the sun. But just imagine, if you go as far away to see the sun as one of those tiny points of light, what chance would you have of seeing a planet which is so much smaller than a normal star and has no light of its own? Obviously, therefore, detecting planets of other stars is a very difficult matter. There are indirect ways of doing it, but we haven't any definite proof as yet, or haven't done so until now. But very recently, there have been some interesting developments in connection with those weird things known as pulsars. Now, we believe that a pulsar is the result of a colossal supernova explosion, a stellar outburst, in which a very massive star literally blows itself to pieces, leaving only a patch of expanding gas and a small, super-dense core made up of neutrons. I suppose the most famous pulsar is that in the Crab Nebula, in Taurus, the Bull, a patch of expanding gas near the star Zeta Tauri. We call it M1. It was the first entry in the famous catalogue drawn up by Charles Messier way back in 1781. Well, this patch of gas was drawn by the 3rd Earl of Rosse way back in 1845 with his home-made telescope, and it was he who called it the Crab. And here is a modern picture of the Crab, and right in the middle of the Crab Nebula is a pulsar, which is the Crab's powerhouse. Well, we think that pulsars are the result of supernova outbursts, but supernovae are by no means common. The last naked-eye supernova in our galaxy was in 1604. But we have had one naked-eye supernova since then, and that was in 1987 in the galaxy called the Large Cloud of Magellan. And here's a picture of supernova 1987A, rather above the center of the picture. It became quite bright. It's very faint now, but it was the only naked-eye supernova for a long time. Too far south to be seen from here, unfortunately. Now, you wouldn't expect supernovae to be centers of planetary systems, and yet planets have been reported there. When supernova 1987A blazed out, we were joined, as we so often are, by Dr. Paul Murdin. Welcome back, Paul. Now, before we start talking about planets, can you give us the background on pulsars in general?
Well, pulsars are stars. They're about the same mass as the sun, 1.5 times the mass of the sun, perhaps. But the striking thing about them is their small size. If you could superimpose a pulsar as a neutron star upon London, you'd find that it fitted within the orbital motorway M25. That's M for motorway, not M for Messier. Yes, their radius is about 10 kilometers. Another stunning thing about them is that they spin. They have a spinning mechanism. The mechanism shines out from the rotating neutron star, much the same as the mechanism on a lighthouse shines out. And as just as in a lighthouse, as the beam of light passes you, you see a flash. The beam of radio or light that shines out from a pulsar flashes past you as the neutron star spins. The spin comes from the origin of the pulsar in the supernova explosion. The explosion goes off. The core of the star that explodes as the supernova shrinks, and just like an ice skater who pirouettes and draws her arms closer together, shrinks in effect, she goes very much faster as she pirouettes, drawing her arms in. So the core of the star that explodes goes faster. And it may be spinning around perhaps 20, 30, 100 times a second even. And in the Crab Nebula, the pulsar that you mentioned spins and flashes at us 30 times every second.
Well, the first pulsar was identified way back in 1968. And how many are known now?
There are many hundreds. And one strange thing about them is that virtually without exception, they're all slowing down. They're born fast, spinning round, say, 100 times a second, and they radiate their energy because this beam of light or beam of radio waves that shines out from them takes the energy away, and it takes the spin energy of the pulsar away. So they slow down.
But they are not all slow, are they?
No. There are some circumstances in which you can get a pulsar to spin up again. For example, supposing you have a supernova in a binary star. Then the supernova forms a pulsar. and it slows down in the normal course of events. But then the companion star starts evolving, and it gets bigger, and bits of its atmosphere dribble off onto the surface of the spinning pulsar. And as the streams of material impact on the surface of the pulsar, it makes it go faster. Here's a ping pong ball on an axis, and I'm going to blow on the surface of the ping pong ball. So the jet of air hitting the surface of the ping pong ball makes it go faster and faster. The stream of material hitting the surface of the neutron star makes it go faster and faster, and they can spin up to perhaps 1,000 rotations every second. That's very energetic, and the pulsar radiates a very fierce amount of energy as a result. That energy can fall upon the companion star, and it heats it up, starts evaporating it. Material streams off like material streaming off a comet, and it can entirely evaporate the companion. And then we're left with a lone millisecond pulsar on its own. Another possibility which produces a lone millisecond pulsar is that the companion star goes through its normal evolutionary cycle, turns from a blue star into a red supergiant, and then it itself explodes as a supernova, and you're left again with a lone millisecond pulsar. Strangely then, a fast millisecond pulsar is actually a rather old pulsar.
But why are these millisecond pulsars so very important, Paul? Because they are, aren't they?
They are important, and there's quite an industry of radio astronomers studying them. And the reason is that because they're so fast, they're very accurate clocks. They pulse very, very regularly. And because they pulse so regularly in themselves, you can see all sorts of subtle effects if they're moving at all. For example, if you have a pulsar which is in orbit around something, then you can see changes in the pulses as they come towards us. The pulsar has a series of pulses coming towards us, on schedule as it were. As the pulsar moves around the back of the orbit, it creates another train of pulses that's not quite in synchronism with the first train. And as it moves to the front of an orbit, it creates a train of pulses that arrives a little bit too soon because the pulsar is closer to us. So you can map the motions of pulsars, millisecond pulsars, very accurately. And there are quite a lot of radio astronomers who do this. One of them is an astronomer in the United States called Alexander Volshin.
Yes.
And he had the good fortune in 1990 to be working with the Arecibo radio telescope in Puerto Rico while they were making some structural repairs to it. His use of the telescope was restricted a bit by the fact that there were these repairs going on, but he was able to make a survey of the strip of sky immediately above Puerto Rico.
What did he find?
He found in the strip of sky in Virgo, in the constellation Virgo that's right overhead in Puerto Rico, a pulsar, a millisecond pulsar. It was at a distance of 1,500, maybe a little more light years from the Earth, and it had a period of 6.2 milliseconds, so a vibration frequency, a pulsing frequency of 161 cycles per second. If you could hear it, it would sound like the musical note of G below middle G, like the note we're hearing now. But there were some subtleties, Patrick, which you could illustrate for us because of your prowess on the xylophone.
It's a vibraphone, actually.
If the pulsar was on its own, it would sound like a very steady musical note. But if we switch the vibraphone mechanism on, then that illustrates what he heard. A vibrating note in which the frequency changed and oscillated. In fact, there were two vibratos muddled up, one inside the other. And he interpreted that as the pulsar pulled by two bodies in orbit around it. There were two bodies rotating around the pulsar, pulling it from side to side. The pulsar orbiting around the common center of gravity, and thereby changing the time at which the beat of the pulsar was heard by us, giving this kind of vibrato effect. The upshot was that he deduced that there were two other bodies in the system of the pulsar.
And were these two other bodies stars?
No, only the pulsar itself was a star. The pulsar itself has a mass comparable to the mass of the Sun, 1.5 times the mass of the Sun or so. The other two bodies were much more reminiscent of planets than stars. One of them orbited with a period of about a couple of months, and it had a mass nearly 3 times the mass of the Earth. And its separation from the pulsar was about 1/3 of an astronomical unit, 1/3 of the distance between the Earth and the Sun. The second body, quite comparable, a little bit further away, perhaps half an astronomical unit, a little bit heavier, and the period correspondingly longer. So it was a system which is rather reminiscent of the inner parts of our own solar system. In our own solar system, you have the planets Mercury and Venus. And if you superimpose a map of our solar system upon the map of the pulsar system, there's quite a good match.
Very interesting, but was that the end of the story?
As Volshin was able to monitor the pulsar over a further 2 years, up to the beginning of this year, as he announced at the meeting of the International Astronomical Union in The Hague earlier this year to the audience that contained us both, Patrick.
Yes, indeed.
He was able to find a further subtlety. There was a third body in the pulsar system. It lay inside of the other two. Its mass was very much less than the mass of the Earth, reminiscent of the mass of the Moon, and its period was in fact less than a month.
Well, if there are 3 bodies around there, could there be any more, do you think?
There are still some irregularities appearing in the timing of the pulsar, and Volshin said in his lecture that he thought it was possible that there were further bodies that would make themselves known as he continued his monitoring program over a matter of some more years. He would perhaps find planets at the distance of Mars and Jupiter and even beyond.
Yeah, Paul, I take all these points, but I think you've got to agree that the neighbourhood of a pulsar is really at the very last kind of place where you'd expect to find a system of planets. And we did have a false alarm way back in 1990, remember, and that turned out to be a mistake. Do you think that these can be mistakes also?
I think we have to watch that very carefully, and certainly astronomers were skeptical at first, but I think they've been convinced by the following fact. As the 2 heaviest planets orbit the pulsar, they line up and come close together. It happens that for every 3 revolutions of the inner one, there are 2 revolutions of the outer one that bring them back almost exactly to the same configuration, and they're close together again. So as they pass one another close by, they give each other a little tug every 200 days. And this makes them deviate from their circular orbits by just a little bit, but it's a little bit that Volshin can measure. He can see this interaction between them. And it's very hard to think of something that's not planets and not a planetary attraction, an interplanetary attraction that can make such an effect.
Yes, I take the point. But, Paul, if these planets really do exist, have you any idea what they might be like?
I think we should have confidence. These are lumps of cosmic stuff about the size of planets, and I think they've had maybe 1 billion years to evolve to systems and planets that look like the planets in our own solar system. The small one, which is the mass of the Moon, I think we can expect it to look pretty much like the Moon. I think there might be some subtle differences. I think it'll have mountains, and I think it'll have maria, because those are things that come out, as it were, the accretion process that formed the Moon. But the craters on the Moon are from some catastrophic event that took place in the solar system some billions of years ago, and there's no reason to expect that such a thing would have taken place in this system. So maybe this little body A is like the Moon without any craters. As to the other 2, well, they're much like the Earth, I think. They probably have solid surfaces. You might expect them to have a heavy atmosphere like the Earth does, even heavier because they're more massive. But the pulsar is there in the system, and I think that could sweep away the atmosphere so that they no longer exist. They're rather younger than the Earth, and they've got this energetic body nearby, so volcanoes maybe we could expect, all sorts of interesting phenomena of particles hitting the surface and making sort of aurora borealis on the ground, if you like. So very interesting and exotic places to be.
Yes, no, certainly. Well, next important question, Paul. Where do you think they can have come from?
Well, I think you put your finger on the point earlier. I think it's very unlikely that such planets could have survived the really fierce processes that have happened in this planetary system in order to create the pulsar. Supernova explosions, binary stars and so on, I think would wipe out any planets that there were around the progenitor of the pulsar, the star that created it. So I think we have to look to other ways of creating this planetary system. One possibility is that the pulsar was at one time a lone millisecond pulsar wandering its way through the galaxy among that field of stars that you showed us earlier on, and that it encountered another star system with planets. And as it went through, its gravitational force, as it were, attracted those planets away from where they belonged, and it purloined a generation of planets off this other star, and that's perhaps what we see now. I think this is actually a rather unlikely explanation for two reasons. One is it relies on a remarkable coincidence that the pulsar happened to have gone through a planetary system, and secondly, if it did pick up these planets, they would be in long elliptical orbits rather than the circular orbits that we actually see. So I'd be inclined to look for more generic ways of creating these planets, ways that, as it were, grow out of the scenarios that created the pulsar itself. So let's think again of how the millisecond pulsar was formed in the binary system. It evaporated its companion by shining on it. And maybe as this evaporation process took place, maybe there were some scraps of material left over. Not all of the evaporation blew the star into space. Maybe some of the scraps formed rings, a ring around the pulsar, and out of that ring the planets formed. Another possibility is that the companion star blew up as a supernova, but not all the material sped out into space. Some of it fell back and again created a ring and created the planets.
Well, I wonder. Paul, certainly one thing is definite. If these planets really do exist, they must be most remarkable places. Time, I suppose, will tell. Paul, thank you very much. Don't forget, if you want the latest astronomical news, then dial the Sky at Night information line, 0891 800 or dial up CFAX, page 615. And when I come back next month, I'm going to show you the very latest spectacular pictures from the repaired Hubble Space Telescope. So until then, good night.